So last time we started talking about acids and bases, mainly Lewis acids and bases, and today we're going to continue along with that topic, but we're going to start to talk about coordination complexes. So this is a brand new chapter. This is chapter 9 in the book. Go to that. So this chapter is all about coordination chemistry.
So we're done with that acid-base donor chemistry?
Yep.
Just okay. Yeah.
I feel like you guys get enough of that in analytical. Like you see enough of it. I just wanted you to know the basics of like Lewis acid, Lewis base interactions. Okay, so before we go on, we have to define what a coordination complex or coordination compound is. Has anyone ever heard that term before or know what it means?
They typically deal with inorganic compounds, and it's like the metals that have a bunch of ligands attached to them. I wouldn't know how to define this though.
Yep, no, that's exactly it. So what it is it's a compound composed of a metal, atom or ion, and one or more ligands. So hopefully if I get back to campus later this week, I'll do a demonstration where we can show a complex forming. The one that we're going to look at is actually the formation of copper. You might remember it from general chemistry, a copper amine complex, where it goes to kind of like a pale blue to like a deep blue really quick. You guys remember that by any chance or no? Nope. Nope. Well, I'll put it online later so you guys can see it. It's a pretty cool complex. So an example of this is tetraamine, copper 2, that ion, which has this, the formula CuNH3 4 H2O. We put this whole thing in square brackets with a 2+. So it seems kind of weird because in other naming conventions that you learned in general chemistry, you wouldn't have two A's next to one another. In this naming convention, you do. We're going to discuss what these compounds look like, how they form, and then we'll get into the naming convention. So looking at this type of geometry, what is going to be its molecular shape? Oops.
Tetrahedral? No.
We have two of these.
Oh, 2 water. Oh, okay.
The 2 water, 4 amines around a single copper ion.
By octahedral?
Yep, it's an octahedral. The waters do actually come into an effect. The waters do bind to the metal center. So we're going to try our best to draw a 3-dimensional representation on here. So OH, or H2O, NH3, and this whole thing needs to have a 2+ charge. We usually indicate that in the corner. Okay, so a lot of these complexes are octahedral, some are square planar, some are tetrahedral. We'll go over what is the more likely situation based upon the number of d electrons. That makes a big influence. And then eventually we'll also lead into the molecular orbital diagrams. Because if you look, the Lewis structure really isn't that good to describe what's going on here. We put a +2 out here because we want it smeared throughout this complex. Before we get there, though, we have to talk about ligands and what's kind of weird about this structure. Or what looks out of the norm from other like organic complexes that you know?
Got copper in the middle?
Yeah, the copper in it. There's a transition metal there. So that bond there, is it ionic or covalent? So what do you think?
Can't it change depending on the compound we're looking at?
Yeah, it can, but what about specifically this one? Is it ionic or is it covalent?
Probably ionic. No, you kind of have to look at the orbitals, I thought.
Yeah, you do have to look at the orbitals and see what it tells you. Something else you can consider, you can look at electronegativities. I would think most chemists would consider this actually a covalent bond. So the idea that you learn in general chemistry where you have a metal and a non-metal paired up with one another means it's always an ionic bond. That isn't necessarily the case when it comes to transition bonds. Okay? So we're going to have to go into it a little bit deeper than what we learned in general chemistry. So this is another one of those points where we're just going to have to let some stuff go and accept new things. Okay? So let's talk about the nomenclature. Josh, you said something about ligands. Some people say ligands. I don't really know why I see ligand, but does anybody know what a ligand is?
The atom or molecule attached to a transition metal, I guess?
Yeah.
Or
We're just going to say metal in general. But yeah, compounds that attach to a metal center. And the number of points of attachment, it's indicated with a prefix followed by the word dentate. So the number of points of attachment are indicated with a prefix followed by the term dentate. Sorry, I'm going to move this up a little bit. And looking at that amine or that ammonia, how did it attach to the copper atom or the copper ion?
Single bond.
Yeah, single bond, but where does that single bond come from?
The nitrogen.
I'm sorry, John, you're pretty quiet. I couldn't hear you. What'd you say?
The nitrogen.
Yeah, the nitrogen, because what's on that nitrogen? If we draw its Lewis structure,
Lone pair.
it has a lone pair.
yeah, that lone pair. So what we're looking for a lot of times with ligands are lone pairs. And do you remember what type of bond this was called that started with a D?
Degenerate.
Nope. You're thinking PChem. Starts with a D, ends with an ative.
Bond, yeah.
Yeah, dative bonds. There we go. Well, this one's just a bond. So a dative bond, do you remember what the definition of a dative bond was?
With going from high to low, like aluminum. Or is it
Don't even worry about big complicated MO arguments. So what happens to make a dative bond? Or like, I don't know, how does it differ from,
oh, is it because of the d orbital?
Nope, not the d orbital.
No.
Well,
Is it just a sharing? It's a complete sharing of those two lone pairs to
right.
metal.
Exactly. So that's an example of a dative bond where this guy's a radical. Most likely what it'll want to do is pair up with another electron. So this is an example of a dative bond. John, you are right. It happens because of those d orbitals. Without those d orbitals, this interaction wouldn't happen. But we've seen instances where you don't need d orbitals to make it happen. Okay, so often attached via lone pairs. Okay, so a monodentate. And we can have a multidentate. So does anybody know what the word dentate means? It's a Greek word.
Is it hard?
Not hard.
Does it deal with, doesn't dentate, is that something like teeth?
Yeah, means teeth. So
Yeah.
one tooth, many tooth.
All right, that's what I thought.
A monodentate ligand is a ligand that will have one point of attachment. Actually, we'll write out the number of attachment. So a multidentate ligand, how many points of attachment is it going to have?
More than one.
Yep. More than one. Okay, and this is the part where I wish we had a board that it could make you guys go up to. I would draw out a bunch of ligands and I'd ask you if they were multidentate, like what's the dentate that's associated. So we're going to go through each of them individually, but I'm going to ask you guys questions. But no, I missed board work. You guys probably don't.
When you pinned us against each other and you like hand somebody else the chalk.
Yeah. Watching everybody cannibalize one another, it's pretty fun. I still do that in general chemistry. I haven't been able to, but every once in a while, Josh and Maddie were both in the same class with Karan, and everyone would go up to the board and they would hand him the piece of chalk, so he'd have to like solve like 4 problems each time.
Aw.
It was pretty funny.
No, not for Gen Chem. I don't think, was I? Not second semester.
Not second semester, no.
Who'd you have second semester?
I had Simpson, but I don't remember ever sitting next to Karan in Gen Chem.
Mm-hmm. I think it was like your freshman
Intro.
like intro class, like Gen Chem 1.
I see.
What was?
The first class. Did you have Gen Chem with Karan?
Yeah.
Yeah, and everybody would hand him the piece of chalk, go up to the board, and he'd have to like solve 4 problems each time. It's funny.
Don't get me wrong, I totally believe it. I would totally do that to him. Yeah.
I've only ever had one student hand me the chalk.
Me.
Yeah. You're the only one who is gutsy enough to do it. I appreciated that.
I didn't think of it.
Okay, so this ammonia ligand, we have it on there. How many points of attachment is it going to have?
1.
Okay, why do you say 1?
Because it's gonna share that lone pair.
Yep. So 1 point. So what type of ligand is it?
A monodentate.
Yep. Monodentate.
Dentate. Oops.
That's okay. Okay, what about Same thing. But for ethylene, diamine, which is sometimes shortened to just EN. Or if we go by the IUPAC name, 1,2-ethane diamine. So if we go to draw that guy out, it looks like that. How many points of attachment is it going to have?
2.
Yep, 2. So what type of ligand is it? Yep, bidentate. Okay, let's move to a more complicated one that you guys have worked with a ton in analytical chemistry. Am I okay to move this up?
Yep.
Okay. Question. Same thing for EDTA. Anybody remember what EDTA stands for?
Yeah, it's ethylene, diamine, tetra, acetic acid.
Didn't you do your experiment on this?
No,
You didn't?
no. The reason I remember this is because one of the analytical exams, the extra credit question,
Yes, extra credit.
was spell out EDTA, what it means perfectly, and it was the longest thing.
What is
I
that
was to get it.
that you
And I was
looked
like,
at in plastic? What was that chemical you looked at in plastic for that class?
oh, that was BPA.
Oh, that's what I was thinking of.
So the one I said was acetate.
Oh, acetates.
It can be, that's an important point, which we'll talk about in a minute. I'm not drawing correct bond angles. Someone's probably going to get mad at me.
Yeah.
Yeah, with the comments.
Whatever. Yeah. Police are coming.
It looks like you have the tetraacetic acid because those are 4 carboxylic acids you have drawn out. I mean,
Yeah. Oh, like why isn't it an acid?
no, I mean like that is an acid.
It is depending on the pH, right? Like
Yeah.
when you get it off the shelf, it tends to be in a sodium salt. So you usually just pull this off the shelf. So how many points of contact are there for the one that we've drawn here?
8. Oh,
4.
10.
Not 4, not 10, not 8.
Because all of the oxygens,
Mhm.
2, 4, 6, 8, and then the 2 nitrogens.
So the nitrogens definitely.
So how about 10?
That's what I said.
Oh, you did?
Not 10. So oxygens.
There's
Which
4.
of the oxygens is going to bind, or which ones want to bind?
It would just be the 4 outer ones,
Yeah.
the non-double ones.
Because they have that negative formal charge. So how many points of contact do we have?
6.
Yep.
I said that. Just kidding.
Oh, did you? Oops. I heard 8, 4, and 10. So what type of ligand is this?
X.
Yep. Accidentate. However, from analytical chemistry and what Josh was saying, these are carboxylic acid groups. What controls how like this prefix here, what would you experimentally do to control the behavior of this ligand?
The pH.
Yep, pH.
You have to
pH.
target the pKa values of each group.
Yep. And I know you guys did a bunch of different titrations with this in analytical. What did you add to your titration or titrate all the time or titrate?
It would always be some type of metal.
Yep. What'd you say, Tara?
You said a buffer.
Yeah, a buffer. And do you remember, like, did anyone smell the buffer?
No.
I mean, it probably did.
A lot of times, like when we do this in general chemistry, we have them add ammonia to it. So that's like the buffer. And what it does is it abstracts these protons and makes sure that it stays that type of ligand. Because it's pretty cool. It's like Pac-Man. It gobbles up whatever salt you put it with. Or excuse me, whatever cation you put it with. What did you guys use this for? Like, what were you titrating?
We would be getting metal concentrations. That's what we would be solving.
Yeah, we did it for like how hard the water samples were.
Cool. And I think it was like, was it calcium that you guys were looking at?
Yeah.
We looked at everything. We would do nickel, calcium, literally whatever was found in the Allegheny River.
So a lot of good stuff.
I never
Yeah.
want to trade again.
Didn't somebody slip
Everyone
into
did.
the river?
Everyone did. I did. Yeah, I came to class with like half my pants like soaking in mud beat once.
The best part was it wouldn't even do that day. Like we all scrambled for it because we thought it was due on different days. And then we had like extra weeks.
That's part of the fun. So next we're going to talk about a really cool system that I like. They're called crowned ethers and cryptans. So has anyone ever talked about these things before?
Yeah, a little bit.
Okay. What do you know about them?
I know that they're really fancy, big-looking ring-type structures that can go on, and they follow some like numeric equation where it's like by some factor of 8, and it's just like large rings, and then they all like point into the middle to like a nitrogen or not
Right.
nitrogen.
And what do they do? Like, what are they used for?
Aren't they used like for optometry? I know they're big there. Like
Yeah.
they're found inside the body, I think a little bit.
I don't know about that one. I know nothing about like biology in the human body. What I do know is they gobble up cations, and there's something really cool about them, which we'll explain in a minute. So they're cyclic Lewis bases that trap ions. So we have some of these. 18 crown 6 is one that we're going to draw. So that 6 indicates how many oxygens they have. What does the 18 tell us?
Number of carbons.
I think, is it?
Attached.
2, 4, 6, 8, 10, 12. I think it's the total number of atoms in the crown.
Atoms. Okay, so 12 carbons.
Yep. 1, 2, 3, 4, 5. We need one more. Oops. Crap. Is that right? Let's count. 1, 2, 3, 4, 5, 6. Yay, we did it. Okay. Now cryptans are, this is more like a 2D system. Cryptans, this does extend into 3 dimensions. But cryptans, they have, instead of just one ring, they're like a conglomeration of rings. So, for example, cryptan 2, 2, 2. Or sometimes it would be shortened to C22. If we go to draw that one out, there are nitrogens.
It's Krytan.
Yep, Krypton. Oh, wait, there should be a P somewhere in there. P, there we go. Yeah, it should be a CRYPT. And it has 1. So what these 2s indicate are how many oxygens they have. 2. 1, 2, 3. And then there's another one that's going to extend over the top. We're going to draw it in red. There we go. So we're going to look at some data and we're going to see something neat based upon how these things are constructed. And remember, these numbers indicate how many oxygens are in these like chains. What we're going to do is we're going to look at the krypton. I keep forgetting a P for, damn it. We're going to have a bunch of log of Kf values over here. So these are formation constants. With lithium plus, sodium plus, potassium plus, rubidium plus, and cesium plus. Got C211, C221, C222, C322. 7.58, 4.18, 1.8, less than 2, 6.08, 2.26, less than 2, less than 2, 7. Sorry, we'll just scramble this down. And then we'll get to the important point. For 7.30.
Just made a graph.
Yeah, I know. I should have just printed one out. Okay. So when we're talking about a formation, could you guys, what equilibrium are we talking about? So yep. So we got this Kf over here. What's the equilibrium like that we're looking at, and what is the equilibrium constant expression that we're considering?
You're looking at the formation of these metals with the krypton. So the so the reactants would be the metal plus the krypton, and then the product would be the krypton and the metal bound together.
Yep. So if we were to write out an equilibrium constant, what would that look like?
It would be the
Minus
krypton metal complex on top, and then divided by the concentration of the metal divided by the concentration of the krypton.
Yeah. Okay, and notice we're putting log values in here. So does a greater log value mean a greater Kf or a smaller Kf?
Smaller. Greater.
Wait. So just taking the log of this number, it means
Yep.
so it'd just be, yeah, it'd be larger.
Yep. The larger the KF, the larger the log value. When you're thinking of pHs and stuff, it's the opposite. Because it's that negative log, which is a pain in the butt. Okay. So now, let's look at these and let's try and explain what's going on here. So the next question we're going to ask is, what's going on here? So remember, these are indicating like the bridge, how many oxygens are in that krypton, like, and how long the chain is. So could anyone try to explain like why we're seeing this trend? Like as what's happening to the size of the kryptons as we go down?
They're increasing.
Yep, they're getting larger. So why is the binding constant going down for lithium, but it's increasing for rubidium, cesium, and so on?
The atomic radius making the ring bigger slightly. So
Yeah.
it's less,
Yeah.
By making the krypton larger, the larger atoms are going to be able to fit into those spaces, so they're going to bind more readily than, say, smaller atoms such as lithium.
Right. So then, yeah, you're right. Like as that gets bigger, it can accommodate larger ones. But then let's look at some strange ones. Let's look at like for krypton 221, which one has the highest formation constant?
Sodium.
Yeah, sodium. What about for krypton 222?
Potassium.
Mhm.
RB. Oh, so it's going like diagonal.
Yeah, so it's doing this diagonal thing. Why does the krypton 221 do the best for binding sodium? And why does krypton 222 do the best for binding potassium?
Probably something with electronegativity somewhere in there.
Nope, it doesn't have to deal with electronegativity. You were on the right track with what you were saying earlier.
It's like the radius of
Mhm.
the ion is bigger, so the angle would be like better, so it wouldn't snap open.
Right. Yeah. So it can snap on the ones that are the right size, right? You were saying as it got bigger. So specifically, why does krypton 221 do the best for this guy, but get worse for these larger ones?
Just the bond lengths in general of everything combined accommodates sodium the best.
Mm-hmm. Yeah, exactly. So these were actually synthesized to be selective to go after these cations, which is pretty awesome. So it's showing like the power of synthetic chemistry and the ability to go after a target that you want, a specific target, which is pretty cool. So like krypton 221, it does the best for sodium, but as these guys, as we start getting larger, as we look along this way, it does a worse job because those cations can't actually fit into the cavity that's made by the krypton. So I don't know if you've ever seen like those Pac-Man frogs that like eat bugs and stuff, and every once in a while you'll see one with like a mouse trapped in its mouth and it can't swallow it. It's like the same thing. So it's pretty cool. So what's going on here? Basically the cavity size of the krypton matches the ionic radius. And these things were synthetically made to do so. Pretty cool. Okay. So we have an idea about ligands. Are there any questions so far? Okay. So we know what these things look like. We've talked a little bit about their bonding. We're going to get more in depth in that in a different class. Let's talk about how to name these things. Am I okay to move this away?
No.
What was that?
Yep, go for it.
Yep. Like, just really, no!
Absolutely not.
Yes,
Okay. So let's talk about nomenclature. Okay, the first thing that we want to indicate is sometimes ligands are referred to by their old names rather than their IUPAC names. So an example of this is like the ethylene diamine. That's not the true IUPAC name for it, but a lot of people refer to it that way. So sometimes you'll see one way, sometimes you'll see another way. But just to point out, ligands are sometimes referred. Are there two R's in referred?
R-E-F-E-R-R, yeah, that sounds right.
Okay. What I thought. To as old names rather than their proper IUPAC names. Okay. And complexes have their own set of rules. So this is different than what you learn in general chemistry, in organic chemistry when it comes to nomenclature. So complexes have a set of rules for naming. The first rule, which goes against what you learned in general chemistry, how did you name inorganic compounds? Like what are some general rules that you followed?
You go by how long the chain is, the longest chain.
That's for organic complexes. I meant inorganic. I'm sorry. Yep.
You probably want to start with the substituents that are added to it. Typically those will go first, so you'd be like,
I'm sorry, Josh, you were coming in and out. I couldn't hear you too well.
oh, okay. You probably want to start with the substituents or the ligands that are attached to the center metal ion first. So you would be like
Yes.
or whatever it is.
I want something even more general than that. Like, how did you start naming? Like, for example, if I had,
identify what is in the compound first.
Yeah, there we go. Okay, so how would you name this guy?
I identify that as sodium.
Sodium.
Yep. Sodium chloride. So you go by the cation name first, and the anions come second. So first rule is cation name first, followed by anion. So example, diamine silver 1 chloride. Oh, I'm sorry, I put an extra A. I didn't need an extra A. So what's the formula going to be for this complex?
It's going to be
GCl. There'd be
So remember, before we do anything, what part's the cation part?
it's the silver
Not just the silver, what else?
and the diamine.
Yeah, this whole thing's the cation. And that makes the chloride part. I lost my purple. Oh, there it is. All right. What about this part then?
Anion.
Yep. Okay, so now tell me the formula.
Ag with 2 lone pairs and then chloride attached.
Yep, I think you meant amine by lone pairs. Yep.
Yeah.
Like that. So that's the formula. Let's do one more. Potassium. Hexacyanoferrate. Ferrate 3.
So K bracket
Mhm.
ferrate, and then it would be 5. I don't know what.
How many? Hexa? How many?
6.
Yep. Okay, there's something that we still need to do to this. What's the total charge on this system? Or this cation, or anion, excuse me.
That should be a -1
So,
if potassium is +1.
so potassium is +1, right?
Yeah.
Well, and we got this thing. What's the charge on it going to be?
Oh, is that going to be a plus or a -3?
Yep. So remember, this part, the first part, is our cation. Then we have a space and our anion. So most of the time in general chemistry, when we were looking at complexes, the metals were always positive. That isn't the case here. So how many potassiums do we need?
3.
Yeah. Okay, we're going to keep going through examples, and it'll get better as we go along, I promise. 2, charged complexes. Are enclosed in brackets. So additionally, the metals, or the metal is provided first in the formula, but the ligands come first when you name it. So let's say I had, oops, I'll move that up. I had this Tetra, amine, oops, 2 N's, copper, 2 sulfate. Okay. First thing we want to do is we want to decide what's our cation and what's our anion. What is our cation in this case?
Tetra copper.
Yep.
Sulfate. Not the sulfate.
That's the cation. And what's the anion?
Sulfate.
Yep. Okay, so now if we go to write out the formula, how are we going to do that? What's it going to look like?
It's going to be like a bracket.
Bracket.
Copper.
Yep, Cu comes first.
Parentheses NH3 parentheses 4.
Mm-hmm.
And then that'll match with SO4.
Yep. What's the total charge on this system?
+2.
Yep. And what about the sulfate, SO4?
2 minus.
Yep. That one you just have to know, so be familiar with those polyatomic ions. Okay. Sometimes this portion that's in the bracket, that's sometimes called the inner sphere. Some people refer to it that way. Are there any questions so far? Okay, let's keep going then. We got to get through 9 rules. We'll see how many we get to. 3. Prefixes indicate the number of ligands. And there are two sets of prefixes. There are for simple ligands, and there are for complicated ligands. So what I'm going to do, I'm going to move this up. We're going to make a table. We're going to have number of ligands. We're going to have simple prefix. And we're going to have complicated prefix. Okay, so 2, 3, 4, 5. So go up to 10, and I'll move this up when we need it. Actually, maybe we can zoom out a little bit. That's better. Okay, simple prefix for 2.
Di.
Yep, di. 3.
Try.
Yep, try. 4.
Wad.
Tetra.
Yep,
Yeah.
5.
And
Hence, yeah.
and
6.
Hex.
Yep, hexa. 7.
Hept. H-E-P-T. Hept.
Yep, hept. Yep. Hepta. 8.
Octa.
Yep. 9.
Nona.
Yep. 10.
Deca.
Yep. Okay. Now for the complicated part, we add is to some of these or kiss to some of them. So for 2, it would be is. For 3, it's triz. 4 is tetra kiss. 5 is pentakiss. 6 is hexakiss. 7 is heptakiss. 8, octakiss. Sounds like a cool name.
Didn't name your daughter that.
Yeah, exactly. We got a middle name picked out.
Yeah, they sound like Greek warriors.
Yeah, exactly. Some like constellation up there. Okay, so knowing these prefixes is important for naming. Let's look at some examples. Okay, example. Let's do dichloro bis. All right, we're gonna try that again. We're gonna write it way neater. Dichloro bis ethylene diamine cobalt 3. We're going to try to write out the formula for this guy.
One thing that I'm really bad with is when do we put 2 M's in amine and 1 M in amine? Because like I've
So-
seen it with 2 M's and 1 M.
So in this case, we'll talk about that in a second, but when you have an actual, when you have an ammonia, it gets 2 M's. Since this is a full ligand, it doesn't get an extra M.
I see.
All right, can anyone, so this whole thing is actually just a cation. We haven't added an anion name, so this is all one big long chain. Can anyone tell me what the formula is going to look like?
The bracket,
Mm-hmm.
Cl2, parentheses.
Remember, in metal always comes
Oh.
first.
Oh yeah, cobalt parentheses.
Mm-hmm.
Cl2,
I'm going to put the,
C2.
Mhm.
Oh, all right.
We could do that whole thing out, but another way it's shortened is the En. And how many of these ENs do we have?
2.
Yep. And what's the overall charge on this complex? Or let's look at the charge of each of these. What's the cobalt's charge with this name?
The +3.
Yep. We got chlorines, and what's their charge going to be?
-1 each, so
Yep.
-2 overall.
Yep, there's 2 of them. And then we have ENs, and what's the charge on the ethylene diamine?
+2.
Nope, it's a trick question.
No, no charge.
We-
Okay.
We assign it a charge of 0. Okay, so what's going to be the total charge on this complex then?
So +1.
Yep. Or we could have written it like how Josh wanted to, but I was being lazy. What? NH2, CH2, CH2, NH2, two of those, Cl2 plus. Either one is completely acceptable. I just tend to write this one because I'm lazy.
And so En represents ethylene diamine.
Yes. So there's a table in chapter 9 that shows common ligands and like their shortened form. Like my favorite one, ACAC. We'll talk about that in a little bit. But there are shortened ones. So I'll show you another example. So tris 2 prime bipyridine. Iron 2. So this one again is a charged complex by itself. So what's this one going to look like?
It starts with iron, so Fe.
Yep, bracket
Bracket
Fe.
F.
Tris, what's that mean?
3.
3, and it's bipyridine, so you could do bipi. Now, what's the overall charge going to be?
Will it be +2?
Yep, it'll be +2. So ligands, if they aren't like halogens, like for example water or ammonia, if they're a neutral molecule, they will have a neutral oxidation state in a transition metal complex. Or we could have written it as Fe C10 H8 N2 3 2 plus. Either one's completely acceptable, but I would probably go with this one because I don't have to write as much stuff. Make sense? Okay. Any questions so far? Next rule. Ligands are written in alphabetical order. According to the ligand name and not the prefix. Okay, so now we're going to do the opposite of what we have been doing. We have a complex written down. I want you to tell me the name. So first, let's identify a couple things. Let's identify the ligands that we have.
We have amine and we have chlorine.
Right. So we have,
And so amine's going to go first.
yep. So,
So
yep. And then we have, what do we have? We have chlor. That gives us a chloro. So we have amine. How many of them do we got?
so tetraamine,
Yep. Next.
dichloro,
Yep. And then what's going to come at the end?
cobalt,
Yep. So we got cobalt. We have to determine its oxidation state. What's the oxidation state of the amines?
+1
Nope.
of the amine.
Yep, of the
Oh,
amine.
no, that'd be nothing.
Yep. That's 0 for that guy. Chlorine?
-1.
-1.
-1. So we got 2 of them. This guy is 0. Whatever the charge is on the chlorine has to add up to be +1. So what's going to be the oxidation state of the cobalt?
3.
Yep. So tetraamine dichlorocobalt 3.
Without spaces, that would all be like one word.
Yep, that's all one word. Okay. What about this guy? So this is these are meant to be brackets. Or not, I'm sorry, not brackets, parentheses. So let's look at the ligands we got. NH3, what's that going to look like in the complex name?
Amine,
Yep. ER?
bromo,
Yep.
and then chloro.
And then this guy?
Would that be methylamine?
Yep, methylamine. Okay. Slap it together. Tell me what the name of this thing is going to be.
Amine, bromo, chloro, methylamine.
Mm-hmm. Bromo, chloro.
That one has 2 M's because
Yep, this one has 2 M's because it's a ammonia by itself. And then we need the metal name. So what's the metal?
Platinum. Or
Yeah.
platinum. Or no, it is.
Platinum, and then we need its oxidation state.
Is it 2?
Yep, it's 2. How'd you get 2, John?
The bromo and chloro are the only things that would carry a charge.
Yep, and these guys each have 0. Fun name. Okay. Can I keep moving along?
5 more to go.
Any questions so far? Okay, number 5 is a pretty easy rule. Anionic ligands. So things with a negative charge are given the suffix O, so they'll end in O. Like, so notice bromo, chloro, they were negatively charged, they have an O. Neutral ligands usually keep their names. We've seen an exception for this though. Water becomes aqua. And ammonia, oops, need 2 M's. It becomes amine with 2 M's rather than amine. So something that can
Why
help
does
you-
it have 2 M's?
Why does it have 2 M's? So it's just so, like, for example, when we're looking at this system, we know what's bound where in a way, and that when we see amine, that means it's just, okay, this is a ligand by itself. Or if we see like methylamine, we know that this portion along here, along here, is talking about that guy. So it's
Okay.
I hope
Yep.
to make it a little more clear. If you want to know some of the names of some of the other ones, check out table 9.2 in our book. This should have a lot of the names. Okay. Any questions with that one?
Nope.
Number 6. There are 2 systems that exist for determining the oxidation state or the charge on the complex. So 2 systems exist for designating charge of complex or oxidation state of the metal. We'll talk about those 2 systems in a second, but additionally, if the charge is negative, you add 8 to the end. So if charge of complex is negative, the suffix 8 is added to the name. So there, like we said, there are 2 systems. One is known as the Stock system. The other one is known as the Ewing-Bassett system, and we're going to talk about both of those. Am I okay to move this up? Yeah. All right. Don't worry. So, 2 systems. You're probably more familiar with the stock system. So in this one, you put the oxidation state of the metal after the metal's name. Oxidation state of metal as a Roman numeral. After the metal name. This one tends to be the more common practice, but there is a drawback to it. It doesn't work well in systems where the charge is ambiguous or difficult to determine. So like where you have multiple metals paired up with one another, or if the complex itself looks really strange, or you don't have a way to determine what the charge is on that metal set. So, does not work well. When the oxidation state is ambiguous and difficult to determine. Okay. Now the other system, the Ewing Bassett system. In this case, the charge of the complex is put in parentheses after the name of the metal, but it's not a Roman numeral, it's just a number. So, charge of complex, not the metal, not on the charge on the metal, but the charge on the complex is in parentheses. Oh my God. That's terrible. We're just going to do that. After the name of the metal. And the benefit and the con to this is it's ambiguous for the identification of the species. Or excuse me, it's unambiguous. Yeah, no, it's ambiguous. We'll leave it like that. Okay, so let's look at an example. Let's name this with both of the systems. We'll first do the stock, then we'll do the EB system. So example. This system, let's name it. So could anyone tell me the name of this complex with the stock system?
Would it be tetraamine,
Mm-hmm.
platinum, 2?
Yep. Sorry, this should be one word. And the 2, how do we specify the 2?
Roman numeral.
Roman numeral.
So in the EB system, how would that be different? We got the same exact name, but now we want the charge on the whole complex. What's the charge on the whole complex?
That's 2.
Yep. So we would write 2+ here. Let's look at a more complicated system. Oops. That guy. PTCl6 with a 2- charge.
Hexachloro platinum 4, so IV.
Not platinum. What's
Nope.
the charge on this complex?
2-.
2-.
So hexachloroplatinate.
Yep. And what's going to be the oxidation state of that metal?
2.
Not 2.
4.
Yep, 4.
So IV. Yeah.
So what about in the EB system? What would that name be?
Hexachloroplatinate 4+.
Now remember, it's the total charge on the complex.
Oh, 2-.
Yep.
Uh,
There you go. Okay. Let's cover one more rule, and we're up to number 6, so we'll have 2 left next time. 7. Prefixes designate adjacent cis and opposing or opposite. Trans geometric locations. So let's consider the square planar complex. I'm going to move this up. Am I okay to do that? So we got these 2 complexes. Let's try and name them. Let's name the left one first. So what type of
Are
ligand?
these locked into a plane?
Yep, they're flat. Yep, they're square planar.
do you want the actual name? Because like,
I want the IUPAC name, not the.
Okay, I was gonna say
Because you know what this compound is, right? What is it?
yeah, cisplatin.
Yep. Yeah. Well, let's go with the IUPAC name.
Yeah.
So first, what do we got to do first?
Point out the ligands.
Yep, point out the ligands. What ligands do we got?
Amine.
Yep, we got NH3, so we got. And what
I-
else?
And
Yep, we got
chloro.
2 of them. So we got diamine.
And dichloro.
Yep. So which one's going to come first? The diamine or the dichloro?
Diamine.
I mean,
So we got diamine, dichloro. What's going to come next?
The platinum.
Yep.
Cis. Oh, well.
And
And it would
then
be beginning.
We want to go with the stock system here. So what's going to be the oxidation state of that platinum?
2.
Yep. But we have to indicate its geometry. So how would we differ? If we write both of these out, they're going to have that same.
So cis is going to go out front and to the left, so it'll be cis diamine dichloro.
Yep.
While trans will be on the second one.
Yep. So we'll do cis and trans, and that's good enough to indicate the isomerism here. Okay. Does that make sense?
Yep.
Okay. Your guys' classroom assignment, I'm going to put on Moodle, but it goes through all of these naming conventions. There might be a couple of them that are more taxing and difficult to do. I don't know if we've gotten to all the rules, but I'll make sure to check that. You want to be sure to practice this and know this for the next exam. Okay?
Are we going to get like prefixes on our test as like a reference, or
No.
like for like pyridine and like the ethylene, amine, like we're not getting any of that? No?
Nope, not getting any of that. Okay? All right. Any other questions?